Quantum mechanics is supposed to be our best theory of physics. That's because it can tell us what will happen in any experiment we've tried. But science is also meant to tell us why things happen. Quantum mechanics doesn't give us why because we still don't understand how to interpret its meaning at all. For example, when an object starts at A and ends up at B, does quantum mechanics say it goes all possible ways at once? Or that there are many copies of each object in many different universes, all going a different way? Or does it say that it doesn't even make sense to talk about an object when we're not looking at it? These are all possible ways to interpret quantum mechanics, at least on face value. We're going to look at the basic rules of quantum mechanics to understand why its meaning is so evasive. Nice of you to join us. Take a seat. Harold, settle down. Let's look at an experiment that showed that nature has a very strange rule. Objects act differently when they're not being measured. Before we get to that though, we need to understand when objects are and aren't being measured. So let's look at a familiar situation. You've lost an object, but you're sure you left it either here or here. You're not currently measuring its position yourself because you're not looking to see where it is. However, consider all the things that are measuring it. For example, think about the light particles that are bouncing off your object. They're basically taking a photo of where your object is. Or what about the air molecules that would have gone straight through where your object is if it wasn't there, but are now bouncing off that position? They're also measuring your object's real position. And that's how it usually is. Objects are constantly being measured by other things. So this statement that objects act differently when they're not being measured doesn't apply for everyday objects, which is why we didn't notice this rule for such a long time. But then I started to look at very small objects like electrons. Things like air molecules and light aren't constantly hitting them because they're small enough to fit in the gaps. So, what exactly are objects like that doing when no one's watching? Let's get back to this scenario where our object, in this case our electron, is either in this space or this space. We expect that objects can only be in one place at a time. Even if you don't know where that place is, you know it's in one of the places. You just don't know which, and this is usually true. But in the case where nothing at all is measuring our object, like our electron, the following will show us that this isn't true. The electron can't be in one place at a time while it's not being measured. This experiment is called the double slit experiment, and here's how it goes. I'm going to fire electrons one at a time from here. When they get to this back wall, the place where the electron hits will light up. How do we make a wall that lights up on contact with electrons? The physics is a two-step process. 1, find one of those experimentalist people. And 2, ask for their experimental physics magic to help you. Simple. The point is, we know where the particle starts and somehow where it ends. But in the middle we don't measure it, and hopefully nothing else is too. Then, put a barrier with 2 doors in it. Obviously there's a good chance that electrons fired at this barrier won't make it, so we're just going to ignore any that don't get through. The electrons that do get through must have gone via the doors. We'd expect that it went through one of these doors, it's just that we don't know which. But we'll see, while the electron isn't being measured by anything, this isn't the case. It doesn't go through a single door. To show this, we're going to show where the electrons would have landed if they acted as we expected, and see that it's different from the actual result of this experiment. To get our prediction, we need to know what an electron that definitely went through only one door would do. So let's close one door and actually do this experiment. As you can see, electrons going through this door end up in a pile behind the door. And of course, if we had done it with the other door open instead, then similarly, electrons would end up behind that door in a bunch. So if we know an electron goes through one of the doors, then we know approximately where it will land. Now, say both doors are open, and we predict each electron will go through one door. We're going to make sure that electrons are fired slowly enough so that different electrons can't go through together and interact with each other. Now, I predict that some of our electrons will go through this door, but we know electrons going through this door end up here, because that's what happened in the single door experiment. And similarly, others will go through the other door and end up here. So, if each electron goes through one door, then we must get two piles. And yet, this prediction is completely wrong. We have to conclude that the electrons didn't go through just one door each. But I know what some of you are thinking. Then they must have gone through both. In other words, the electron quite literally gets cut in two. Parts of its mass go one way, and the other part the other way. Then these two parts of the object bump into each other and ricochet wildly, causing the weird pattern. Or, in some versions of this explanation, the particle splits into two and then flattens out into two waves that interfere with each other. Unfortunately, there are many problems with these sorts of explanations. Firstly, if it splits into two bits, or if it spreads out, then when you measure it at the wall, you'd expect to get two dots, or a smear spread out. But that's not what happens. One electron through gives you one crisp dot. But I believe a more complicated version of this wave story to get around this. That goes, it's a wave when you're not looking at it, but when you measure it, it becomes a particle again. That would mean that as soon as the electron hits the back wall, it has to immediately pick up all of its mass from everywhere it's spread out to and gather into a particle again. But moving mass needs energy. Where's the electron supposed to get that from? There is a sense that waves are involved in this experiment, but it's much, much more subtle than you may have been led to believe. Anyway, the point is the double slit experiment showed me some important things. When nothing watches what an object does, it doesn't just do one of the options. We can't see that directly, but we can infer that from the experiment. And the object doesn't physically split up and have parts of itself do each of these options. So, what exactly is the object doing behind our backs? And how are we supposed to predict the results of this experiment? They're crazy. And it isn't just the double slit experiment that had unexpected results, by the way. Loads of other experiments showed that particles are doing something really strange when we're not looking at them. And that's why I specialised in quantum mechanics. It's some nice maths that you can tell an experiment to, and it tells you what you can expect. And so far, it's always been right, which is a grand achievement. But I still want to know what these particles are actually doing. But this quantum mechanics doesn't tell us. It's just a bunch of maths after all. In fact, some physicists say that it doesn't even make sense to talk about an object when it's not being measured, that it doesn't exist. This seems crazy to me. Recently, more physicists have started to take this question again, and they've even started to tease meaning out of this mathematics. It's a really exciting time to be asking questions about this theory. Isn't it, Harold? Right, everyone. I'm sure you all have classes to attend. Off you go.